Okay, morning, ladies and gentlemen. Um, thank you for the introduction, Werner. So I'm just going to give you a brief snapshot of what we do in our group, and would like to first and foremost thank the CHPC for making us exist, because most of the work that we do actually would not even be possible without the CHPC. So and they've made available their resources. They've accommodated us with regards to the request times and so on. So our work is quite relevant in the context of today. So we focus mostly on climate modeling, and I'm just going to talk you through um, the type of work that we do and how relevant it is to the conversation of today, especially with regards to climate, weather forecasts, seasonal predictions, um, and also the impact. So just a brief overview. We are part of a group called Holistic Climate Change. That's the impact area for those who know the CSIR. So there's a total of 4 groups in that impact area, and of which climate and air quality modeling is one of the groups. So what we typically involved in is modeling, forecasting climate, and modeling the risk and vulnerability due to the variability and change of climate. And also we provide what we call seamless projections. That means we focused on a range of timescales. I'm going to take you through that so that at least you have an appreciation of what that means. And then what we typically try to do is to provide information that can help decision makers to make informed decision when it comes to adaptation and also mitigation of climate change. And then another aspect of what we do is concerning air quality. So we also have an aspect of that. As you know, air quality and climate are almost two sides of the same coin. So, and then we try to also understand the impact of air quality on nature, on human health, etc. And then what do we mean by seamless forecasting? It means we model or we forecast on a range of timescales. So, for example, the typical weather forecast that you get on television or radio is typically 1 to 3 days. After that, obviously, it becomes a little bit dodgy, but we also do that. And then we have what we call medium range forecast, and this is actually what we've seen uh, to be actually a lot popular these days. So we try to look into the future in terms of what the season is going to look like, say 3 months down the line, 4 months down the line. And you can imagine what impact that has on, let's say, a farmer who wants to plan their cropping season. And then the next range is over years, say 5 years. We look into the future, into the climate. We've got a lot of indicators that we use to simulate that. And then obviously, the longer time scale over 10 years, 20 years, up to 2100. We've got models up to 2100. So we know approximately what the climate is going to look like in, say, 50 years down the line. And if you are a decision maker, it's obviously something that you would like to know, so that you plan how you adapt. Because the reality is that the climate is changing, and yeah, there's a lot that still needs to be done, even with regards to the modeling forecast themselves. But at least we get a sneak preview into the future. So we typically build what we call climate information systems, which creates strategic advantages for certain entities that take this body of work seriously. And then I'm just going to give a brief overview into the numerical weather prediction. So this is what you get typically when you look at the weather forecast. So we currently run 3 different models. CCAM, that's the most popular one, the one that is operationalized. And then the weather research and forecasting model, which is in the testing phase. And then also the regional climate model. So, and as I said, these have been made possible by the CHPC. So what we try to do is just to compare what the difference is between the 3 models. And yeah, we've utilized quite a lot, although it could be more of CPU time at the CHPC. I'm not going to go into details here, but these are basically the underlying equations that govern the models, the weather research and forecasting models, and also the CCAM model. So it's basically a coupled equations of momentum, pressure, and also conservation of water and energy. And these equations, HPCs, are needed to solve these equations accurately, so we can be able to simulate the atmospheric conditions in advance. And if you look at the comparison between the three models, so you can look at the CCAM, WRF model, and the regional climate model. We can see that basically they predict very, very similar results. I can say that the WRF model and the CCAM model are actually quite close to each other in terms of what they predict. So what this tells us is that we are probably on the right track with regards to the modeling philosophies that are actually incorporated into these three models. And then the results were also comparable with what was observed in terms of the measurement. So we do have also observational measurements that we also rely on to validate these models. And also the same picture goes for rainfall. The first one was the temperature. So for rainfall patterns, it's also almost the same picture. However, there are certain constraints that we're facing, and I'm sure the CHPC colleagues are quite aware of it. The load shedding has impacted on the operations of the CHPC, so we're facing a little bit of constraint in terms of what we can do on the CHPC. There has to be a reduction in the number of queues that we can load onto the platform. And also there are storage limitations. That means we cannot keep our numerical weather production products for long. And therefore we have to really remove runs as we go along to make space for other runs. But otherwise, when everything is functioning seamlessly, this is a wonderful piece of equipment to have, and we rely heavily on the CHPC to assist us on that. And then with regards to seasonal forecasting, so seasonal forecasting is over a few months ahead. We've also actually tracked, I think we've all experienced some of these events. If you remember in Pretoria, in Centurion, they were flooding, I think a couple of years back. I think it was 3 years back. We managed to track the cyclone that was actually responsible for these cyclones, for this flooding. And then also this is a picture of this is Cabora Bassa Dam in Mozambique, which was actually also spilled over because of the impact of the cyclone. And then cutoff flows, we also investigate them. We also track them. These are systems that cause torrential rains over the winter period after summer, and then the tropical temperate troughs. Also, rain-bearing systems that are responsible for rain in the summer. So we also managed to track these systems. And then tropical cyclones, as I've indicated previously. And then on the seasonal forecasting system, we do a 50-kilometer resolution, global climate models. And yeah, these are basically essential tools for climate change adaptation that assist in climate hazard risk management. So we do this for we've got projects with certain clients that are interested in seasonal forecasts. And this is basically to help them to plan either for the energy. ESCOM is one of our clients. They want to do energy planning. So they want to know basically what the weather is going to look like, what the temperatures are going to look like, and how the hydroelectric power plants are going to operate, and so on. So for that, we do seasonal forecasts for them as well. And then this is just an indication of the forecast for this year, May to July. I'm not going to go into much details here, but then we rely on the National Center for Environmental Prediction, which was the one that actually developed the WRF model, but they also provide us with the boundary conditions for the atmospheric states for the seasonal forecast that we undertake. And then this is for June to August and July to September. And all these simulations were actually verified. They're very, very accurate with what was observed in terms of the weather forecast. So you can see that you've got a dry tendency and a wet tendency in certain regions. And if you couple that with a measurement, we can actually verify these models. And then the other body of work that we do is to try and predict the state of droughts into the future as well. So if you look, this is just an animation that is looking at how the rainfall patterns are going to evolve over a period of 100 years. And these are just the two indicators. There's a slight difference between these two indicators. This one, I think, is the one that's more accurate because it also factors in evaporation. And it actually predicts a more dire picture than the SPI. This is a standard precipitation index. So if you factor in evaporation, you can see that the picture is a bit more worse than actually it is predicted by the SPI. So I tend to rely on this picture more because it's a bit more realistic. And then in terms of the climate change impacts, like I've already indicated, we've done simulations from 1961 up to 2100. We've done 6 global climate models, which we've downscaled, and we've used 2 scenarios, of which I think one of them is indicated there, which is RCP 8.5. This is what we call the worst case scenario. In other words, if we continue as we are living on this planet without doing any mitigation for greenhouse gas emissions, what is going to happen? And the picture is actually not looking good in terms of the temperature increases. And then we've also downscaled. Downscaling, it basically what it means is that we zoom into a certain region and then we discretize at a higher resolution. So we've downscaled to 8 kilometers. The global climate models, they're typically 50-kilometer resolutions. And then we downscale to 8 kilometers if we want to get more accurate results for certain regions. And then this requires quite a lot of computational power. And we rely especially on the CHPC to do that. And then with regards to the outlook into the future, we can see for West Africa, for example, this is what is predicted for the rainfall regime. For East Africa as well, there's a slight increase in rainfall in the rainfall patterns. And then for Southeast Africa, there's going to be a net decrease up to 2100. So Southeast Africa is actually going to be more direly affected by climate change, and this is what we've sort of gleaned from what we call the CMAP 5 experiments are the previous generations of climate models that we're using. Currently, we are looking at downscaling the CMAP 6. CMAP 6 is the new generation of climate models, and we are starting to downscale them. They've got more realistic picture of what is going to be experienced. And as you know, these climate models, they evolve each and every year. So we are looking forward to the results that will be demonstrated by the CMAP 5 models. And then our work also feeds into certain work that is also done within the CSIR. So I don't know if you've heard of the Green Book. The Green Book is a platform that's actually popular with the government and private sector. What it does is basically it tries to look at the adaptation measures and the effects on the communities of climate change. So it looks at the whole of South Africa, and then you can zoom into a particular municipality and look into the future. And then with just a few clicks, you can look at how vulnerable certain communities are to climate change. And the work that we've done actually underlies what is in the Green Book. So the climate models that we've worked on are embedded into this system, but also we're looking at improving the Green Book itself in terms of the functionalities, and also improving on the models as well to use the more modern CMAP 6 runs. And then there's a project called Focus Africa, which is a collaborative project that looks at the Southern African region. And also I think Mauritius is involved. So it looks at case studies of what is going to happen with the climate of Southern African countries in terms of infrastructure, in terms of energy, water resources, and agriculture. So for South Africa is also part of this case study. And for South Africa, if I'm not mistaken, we're looking at water resources. And then also for Mauritius, the same thing. And then this work also feeds into the NDC reports. So NDC is the National Development Communication for South Africa. So we used these models to feed into these reports in terms of our obligations as South Africa. And then we've got a PhD student who is working on what we call paleoclimate. Paleoclimate is basically looking way, way back into the past. And Puli, I think, is here. He can answer questions with regards to that. So the reason why we do paleoclimate, you'd ask, why are we looking thousands or millions of years into the past? Is because we want to verify that the climate models that we're using currently are able to predict what was happening also in the past. So once we actually show that, yes, these climate models give a picture of what was happening thousands of years ago, then it gives us confidence that even if we predict 100 years into the future, we have reliable results. So these are some of the results that emanated from this research, and it can be seen here using the Copenhagen maps, which is basically this disaggregation of the climate system into five groups, and it is evident that the what we call the last glacial maximum, this is the paleoclimatic conditions were actually colder than what is being experienced now. And then, the reason why we even bother with all this is because we've seen that there's a possibility of multi-year droughts. I think all of us have heard of almost the day zero that almost happened in Cape Town. These are extreme events. These are events that probably have not yet been seen, even in the past. So we've also seen intense tropical cyclones that have threatened the southern part of Africa, and this pose a threat to the livelihoods of this region. And then, in terms of the Sustainable Policy 1.5 from the IPCC, there's also elevated changes of agricultural drought, heat stress, and heat tolerance of crops. There's a risk of floods. I think we've all can attest to that. Occurrence of fires. This is not an accident. This is a result of climate change. And it would actually be beneficial to have more accurate models that actually look more into what is expected, because it is going to get, probably is going to get worse than it is if really nothing is done. And then the direct impact of extreme weather events on various sectors of the economy. I'm going to talk a little bit more to that. But before that, maybe let me just articulate, because we're at the CSIR, we're interested in novelty of work. So that means we want to convert the climate data into tailored information and data products. That means we wanted to tailor the information to specific sectors. So if it's ESCOM, we tailor the information to what ESCOM requires. If it's an agricultural farmer, we tailor it to what they want in terms of the early warning systems, how they plan their planting season, how they plan the drought resilience crops and so on. And then publications. This is also an important part of our work. Knowledge creation and climate services and diversity. So we pilot the creation of climate information system, which will be better in a better position to adapt for the continent to adapt to climate change. And then strategic partnerships. These are all basically KPIs of the CSR. I think we all know them. So we've got international partners and also local partners that are interested in the body of work that we do, and also they help us to develop our capabilities. And then just to reiterate, so for transport, these are basically what we can say the priority areas that are most reliant on the climate services or climate information systems that we develop. So transport, for example, Transnet, they've shown really an interest in what's happening at the port areas. So sea level rise is a big threat to their operations. Not to mention the extreme weather events that happened, for example, in KZN, and even inland as well. So agriculture, I've already mentioned. This is an important sector which is badly affected by climate change. Energy is another one in terms of the generation of energy, and also the dependence or the resistance of the infrastructure to climate change. And then for government, we've got certain projects where we assist them in terms of their policy development. So, for example, the NDC that I mentioned is a DFFE initiative that we assisted them with. And then increasingly, we've seen that the banking sector is taking a big interest in climate information. So, for example, the claims that arise as a result of not only extreme weather event, but a simple thing like a geyser burst, for example. How is it related to a weather, to the prevailing weather conditions? So the banks have actually noticed that there've been a spike of these kind of claims that never used to happen in the past, and they're trying to link that to the changing climate. And we are trying to figure out through our modeling expertise how to relate to that. The insurance industry, I'm not even going to even mention that. That's an obvious one. The extreme weather events have wreaked havoc with the insurance industry, and they're scrambling now to actually find adaptive solutions, or even to see how they can avoid some of these claims that are now related to climate change. And yeah, we do this through interactive workshops, dashboards. For Eskom, for example, we issue weather bulletins, and then cloud-hosted portals and reports. So that's basically our channel of communication. And then what is it that's driving the research? How can we improve the confidence in the models? As you know, models are models. They can be accurate, they can be inaccurate, depending on the assumptions that you make. And we would like to ensure that the assumptions that are embedded in the models are as accurate and as representative as possible. That's why we have all the time improvement in the different climate models. And then what are the climate-induced tipping points for sectors of development most likely to be felt? So tipping points are basically points where really it's difficult to reverse the impacts of climate change. And this is what is driving some of our research policy or research direction. And then what are the Southern Hemisphere climate change drivers? We need a strengthened Earth system science model in Southern Africa, or basically in Africa as a whole. We do not have this currently, but there's work in progress. In fact, this work was started actually at the CSIR some years back. It's still under development, but I think it will help this region if we can actually develop a model that is particular to this region, that is peculiar to this region, and then we can have a more accurate representation of what we are going to experience in the future. Currently, we rely on models that have been developed elsewhere, specifically by the CSIRO in Australia. And then how best can we inform adaptation options? This is the critical question that is burning, I think, through almost all the economic sectors that we've encountered. And then in terms of air quality modeling, we also look at sources of emissions, particulate matter, sulfur dioxide, and NOxes. These are typically pollutants that have an impact either on the health of an individual, or even on the climate itself, and also on other sectors of the economy, like the agricultural sector, for example. So we calculate the dispersion of precursors and concentrations, and we use a model called CCAM. In order to do that, this is basically a conversion model. And then we try to apply that to certain urban environments where we develop what we call urban heat maps, or basically air quality planning for metropolitan areas. And we've done this for city of Joburg, city of Tshwane, and city of Ekurhuleni, as well as the Vaal Triangle air quality management region. So in terms of the usage of CHPC, I'm just going to run through this. We've used 1.3 million cores. This is quite intensive. The wolf model that we run is scalable, 48 to 240 cores. It takes about 20 days to simulate a year of air quality models. And then in terms of the CCAM, which is not as scalable, we use up to 72 cores. But because of also restrictions, we can only do 3 to 4 months at a time. We would have liked to run 12 months, but it's not possible currently with the constraints of the CHPC. And then my next slide is probably my second last one. So just an example of what we call PM particulate matter 2.5 micron over the Gauteng region. This is Gauteng and Ekurhuleni, Tshwane, city of Joburg. So you can see that by and large the PM 2.5 is exceeded throughout this whole region. Therefore, there needs to be a proper mitigation plan in place. And the same for the Vaal Triangle airshed priority area, which we also developed. And also the red areas here indicate that these are areas of concern for PM 2.5. And PM 2.5 has been linked to a number of health impacts, especially lung cancer. So I think this needs to be managed quite carefully. So I think that's my last slide. Thank you, ladies and gentlemen.
I maybe have a quick question, but perhaps the answer is going to be too complicated. So you mentioned, so how much is the accuracy of the weather prediction over for example, the months? Which is the accuracy of the prediction? How does the accuracy of the prediction changes when you expand the time at which you look at the prediction? So from few days to few months to few years. And if you want to improve that accuracy, what is missing currently in the model? So how you can improve them?
Okay, yeah, I think this is a question that has always been there. With numerical weather prediction, we know that only up to 3 days. That's why I indicated 3 days. You can say with a certain level of accuracy. When you get to 5 days, a week later, it's no longer that accurate. But we do multi-scale forecasting. So we do also seasonal forecasting. So on I think every 3 months we update the seasonal forecast model, and then also we do yearly forecasts. So you can ask, then if you cannot forecast in the next 7 days, how can you be sure that in the next year or the next 10 years you're accurate? That's your question, I believe. Yeah, I think the way around it, how we go around it, is that we use different models for the different. In fact, it's the same underlying models, but it's different conditions that we simulate, the boundary conditions, the forcing mechanisms in the different timescales. So for the same timescale, you cannot do, you can only forecast up to a certain level. And then you have to use a different model if you want to do seasonal forecasting. That's the only way that we go around it. But in order how to make it more accurate in that perspective, I think this is research that is still ongoing. If you look at numerical weather prediction, the more the resolution is increased. Basically, that's a way how to make it also accurate. But yeah, also the models, because it's a model, it's got assumptions. You can never be too sure. But we're trying to do 2 things: to use more computational power and also more better resolutions. That way, we try to improve the accuracy of the models.
Great. Okay, let's thank Njabulo one more time.